Hi, Songhan and Z. I'm looking at your shear assignment, and there's a couple things I wanted you to adjust before I grade it. Um, so this is one thing that's, when I was thinking about how to do this semester, I've said a bunch of times that I'm trying to be more. I'm just giving you an option of an answer that you can sort of use as a reference. And what a lot of people are doing is what you're doing is basically trying to copy it, which is okay. But I see that you're not getting all the concepts when you do that, and you know, that's a downside to this. So there's a few things you need to understand here before you can move on, um, or really maybe even just one. What we're doing here, so um, this is your modeler. What we're doing here is we're taking the data and we're first off trying to see if it is good enough to use. In other words, does it make sense to us? And that's why um, we're comparing it to the theory. And so your orange or your yellow line here represents theory, and so does your gray line. And I'm not sure if you get what the theory is. It's pretty simple, but let's just so just to be clear, we're saying, let me change this. We're saying that shear strength or shear stress equals the load. Let's put it up here, I guess, for now. Just trying to write it out with my little app. Divided by the area parallel to the load. And all that means is that we're essentially using the same equation as we did for tension and pure compression, but that if you look at the video I made, the idea is that the material that's being loaded in this pin and the joint is actually parallel to the load. And so it's that even though the simple equation is the same, the way the material is experiencing the load is completely different. It's going through um, it's going parallel to the material as opposed to normal to it. And so if you can ask me or you can draw that out, you need to understand that. So that's the first question as to whether or not this our theory matches our um, data. And that's what this chart is here, right? Oops, let me stop this. That's what this chart is about. So the yellow line is theory. You plotted um, the load over the area. And if since shear stress is a material property, it should be a constant. That means it should be linear and it should be basically a 45-degree angle like this. As we increase the area, we should increase the load that the material can take. And that's what you were doing over here. You were plotting these. We just made this up sort of and just doubled everything to get that line. Um, we also had a theoretical shear stress we looked up, and that's what this gray line was. We just plotted. You might have plotted 39,550. In these links over here, we basically said 40,000 was about what it was. So, or maybe you plotted. I think you just copied me. I plotted the 40.6, and then so we have then the shear in the gray plotted, and the load versus area, a different way of plotting it, in the yellow. And then we plotted the data to compare to those things. And so the orange, those theoretical lines, the orange is our data shear. So it's the shear values that we calculated, that you guys calculated. And then here it's just the load versus the cross-sectional area in blue, so the orange and blue. And we basically were trying to figure out whether or not they, first of all, just looking at them, they look pretty similar. There's something going on with the shear stress where, and we knew that up here, that these should just be the same, and there's some variation. We'd have to explain that if we were doing like this in a professional situation. Um, but it's not that far off. And then when I compare it to the load versus area theoretical yellow line to the blue, it really looks pretty close. And then we did a theoretical, a statistical analysis. Um, and if you don't understand, you should ask me. But the CV of the data is basically that's a statistical comparison or comparison between the standard deviation and the mean. And you should just look up whether or not the point oh 0.06 seems like a good number. It from my, and I'm not a statistician, that seems pretty close to me. So that means that that's one indication that the data is pretty good, just the data itself. Then we say, okay, um, what about how the data compares to the theory? And that's why I think in mine I wrote, let's see if I did. Yeah. You see here how I said percent error theory to data mean. So we're comparing the theory to the data, and we're getting a 7% and a 6% difference, either if it's percent error or percent difference calculation, which I'm saying, okay, that's pretty good too. So I'm kind of feeling pretty good about this data, that it's in it's got the same shape as the theory and the values are pretty close. Now, what about this data mean R squared? What is that? We can see it's right here. You see R squared 0.9946. This is something you can, so the R squared value is something that you use to compare um, essentially a straight line to a trend line for your data. So the R square of of this line right here, this yellow line is 1. But for the data, it's different. So let's select this data set. We're going to format it, and I'm going to display the R squared. So this is what I was looking for. So the 1 would be the data mean for the theory, but that's given. That's not really interesting. What we're trying to do is compare that to the R squared for our data, and we have a 0.9946. That's also pretty good, and you can look that up to see. So what I intended here was 0.9946. Um, so that's the first thing. Secondly, how did I? Okay, so what we're basically saying, what I'm saying is, if I look at this data and I do all these calculations, I can say to myself, the theory and the data are close enough that I can use the data in my experiment or in my design of my truss is what we're getting ready to do. So that's the first thing. Secondly, we want to create a modeler. We want to be able to say, how big does this pin need to be to take a load that's coming to it? And that's what this whole section is down here. And what you guys did is you just typed in my values. So that's not what we want, obviously. And I think you should have known that. You could have asked me. So I'm not sure why you just think you can type these in here and I'm not going to notice it. Um, but anyway, what are we doing here? So if we know that, again, let me turn this guy on. Let's see if that'll work. Yeah. So we already said that. Let's change the size. Let's just delete this and do it again. If tau, which is shear stress, we're calling it, equals P divided by a area parallel, which is kind of confusing. So I'm going to say parallel, which is just the cross-sectional area, but it's oriented differently. So that's why I'm calling it that. Um, then A parallel equals, oops, equals P divided by tau, right? And so that's what you need to do here. Sorry. This here is supposed to be solving. So this tau is our theoretical shear strength, right? That we're getting from the material, either here or here. So 40,000 was close enough. P fail, we're just typing in. It's whatever number we want to use as an example. And we're going to have a factor of safety because we want to be able to adjust it. We want to make the bolt stronger than it needs to be. Then if we just calculate using that equation that we have here, we can calculate a theoretical area that would take the load given this material strength and this load in this equation. And then it's round, right? We said that the pin, is round. It's a little bolt. Sorry, I'm drawing this with my mouse pretty hard. You know, I'm saying that that's in the joint. That's what's taking the load in the joint with our materials. So it's round, so that's where we can get the diameter from the area calculation using the area of a circle. Now, how do I get the data value though? And that's what we're saying. We still want to, at this point, I still wanted to have a data version of this that I can compare. So what's the data version? Well, if I come back over here again to this trend line, I can display its equation. It's just a line. So here's the equation for that, the trend line, the linear trend line for our data um, set, which is the blue dots. And we could use that then. So since y is p and x is the area, then we can use this equation to output an area, right? You can solve for x and then get a pin diameter there. And I did that, and we found that we had a pretty close correlation. And then to get this value, I included a factor of safety, and I in my original uh, assignment version, which is over here again, I said that we can only use 0.125 increments, so which is why I got a 0.25. Anyway, you may need to ask me about that. But my point is, I want you to fix up this, at least get this working as a little calculator. If you don't understand that, then you need to ask me. And I'm not going to grade this until you do that, because that's kind of like the point of this. And you're going to need something like this calculator for your project. Okay? So let me know if you have questions, and of course, I'll help you.